Okay, the next thing we're going to look at is properties of perpendicular lines. Perpendicular lines are lines which meet at a right angle, and in the vast majority of times they've got a property which is if you multiply together their gradients you get a result of -1. So if, for example, we've got a line which has got a gradient of 2, then the line which is perpendicular to that will have a gradient of -1/2. And that's because 2 multiplied by -1/2 is equal to -1. Now, another neat trick with that particular property is you can see that 2 can be written as 2/1, and to get the gradient of the line which is perpendicular, we just flip 2/1 over and change its sign. Now, that works in the vast majority of times. So if, for example, I had a line which was 3/4 for the gradient, then the line which is perpendicular will have a gradient of -4/3. And again, that relationship of the gradients multiplying together to give -1 works again, since that's -12/12, which is -1. So in essence, in the vast majority of times, if we've got a line whereby we know its gradient, to get the gradient of the line which is perpendicular, we flip the fraction over and change its sign. So perpendicular to 3/7 would be -7/3, -2/3 would be 3/2, 5/7 would be -7/5. Now, if I was to say find, for example, the gradient of the line which is perpendicular to a line which is a gradient of -3, then we can think about -3 is -3/1, flip that over, change its sign to positive, and that would be +1/3. So again, what about 7? Well, that could be written as 7/1, so the gradient of the line which is perpendicular would be -1/7. Now, I did say that in the vast majority of times that rule works. The rule falls down when we look at vertical and horizontal lines. So if I was to say that that line was vertical, then we know that a line which is vertical has an undefined gradient, i.e. the gradient is infinite. Well, in terms of making a calculation with infinity multiplied by something equal to -1, that's kind of ill-advised, but by inspection we can see that perpendicular to a line which is vertical is absolutely a line which is horizontal, and a line which is horizontal is equal to 0. So if our gradient is undefined, then the line which is perpendicular has a gradient which is 0, and obviously vice versa is true. So that's the one and only scenario in which we don't lose m1, m2 equals -1. For all other lines, m1, m2 equals -1, which is flip and change the sign, will always work. Okay, so let's look at an example of this. If we've got a point P, which is 2 - 3, and a point Q, which is -1, 6. Find the gradient of a line perpendicular to PQ. Well, first of all, let's find the gradient of the line PQ. So that will be y2 minus y1 over x2 minus x1, and that's 6 minus -3 over -1 minus 2. 6 minus -3 is 6 plus 3, that's 9, over -1 minus 2 is -3, and that will simplify down to -3. I then head up what I'm going to do next, which is to look at the line which is perpendicular with m1, m2 equals -1. The gradient of the line that's perpendicular then, so -3 could be written as -3/1, flip it over and change its sign, and that would give me +1/3. Okay, next let's look at an example 2. Given that K, L and M are the points -5, 0, -2, 3 and 3, -2 respectively, Prove that KLM is right angled at L. Okay, so we need to prove that these lines are perpendicular. So let's first of all find the gradient of KL. So MKL is equal to 3 minus 0 over minus 2 minus 5. So that's 3 over minus 2 minus 5 minus 2 plus 5. That's 3. 3 over 3, and that's equal to 1. Now, I think I can anticipate now that the gradient of this one, if it's perpendicular, should be minus 1, since 1 times minus 1 is equal to minus 1. So let's find out. So gradient LM is equal to, this time, y2 minus y1 minus 2 minus 3 over 3 minus 2. And that's minus 5 over 5, which is equal to minus 1 as expected. So I would then say MKL multiplied by MLM equals minus 1. 1 times minus 1 equals minus 1. Therefore, triangle is right angled at the point L.